Thank you so much for that kind introduction. Yes, my name is Alan Franslivers. I am glad to be here. Thank you to Dr. Fernando Munoz, who has invited me to speak. And I apologize for not being able to present to you in person, but it is we are just recently allowed to travel, and so the invitation came a little bit too early for me. And I must say, though, that my daughter visited Colombia only 2 weeks ago. So I'll say that my Franslivers name was present in Colombia. Okay, very good. Well, my talk to you this morning is about soil test biological activity as an indicator of nitrogen availability. As sugarcane growers, as any kind of industrial commodity growers around the world, we know that nitrogen is vital to agricultural production. It's something that if we don't have enough nitrogen, we don't get the yield production. And so profitability will suffer as well. So we need to have nitrogen in our cropping systems. The issue is that the nitrogen is very leaky in the inorganic form, and that nitrogen can escape to the environment. And so that causes ecological damage. It causes issues with our environment. And of course, it costs growers money when you lose nutrients that you have paid for and then apply them and don't find them. Now, this soil profile picture that I have here, I wanted to explain a little bit is that it's important to know what soil characteristics are to 1 meter or to 2 meters. Those characteristics are important. But I want to say that the vital interface, that surface 10 centimeters of soil, is where the real action is. Because if we want to rely more on nitrogen in the organic form, which or nitrogen cycles from inorganic to organic and then from organic back to inorganic, and if it stays too much in the inorganic, it's of course that's where we want it for plant growth. But if there's too much of it, then it of course is lost to the environment. So that top 10 centimeters is really, really important. And the reason that it's important is because the nitrogen that is in excess leads to water, to loss through water, rivers and in streams. And we see that all around the world, wherever there's industrial agricultural production, that the water bodies are being polluted. And this is a concern because obviously it's not just the land that needs to be produced, but it's also the water bodies. And so this can lead to fish kills, and it can lead to simplification of our ecosystem. And then we have disasters that are led there. So you see that in Colombia in this map doesn't show necessarily a red dot where there's documented hypoxia conditions, although this is already quite an outdated map, but it does indicate that anywhere we have coastal estuaries, there's a risk for nitrogen pollution. And so that's of concern. The other concern is, of course, that commodity prices change. And of course, I've given you here now, not something that you're interested in, you're interested more in sugarcane, but the commodities react similarly in that the commodity for corn, for maize, we have these large fluctuations in the value of that product over time. And of course, we want to have high commodity price so that we can get better return. The issue really is that the costs of the inputs are also very complicated. So in this example here, on the left, this is the cost of nitrogen fertilizer in pounds, dollars per pound. And of course, it doesn't really matter because I'm not able to convert them to pesos per kilogram anyway. But we know that recently the fluctuations in the nitrogen fertilizer price have increased all around the world. And so rather than fluctuation, I should say the increase in nitrogen fertilizer price. But it will fluctuate, and it has fluctuated in history. It will fluctuate again in the future. The issue, though, maybe perhaps a little pessimistic view, is though that whenever commodity prices increase, the input costs often increase as well, but oftentimes the commodity price decreases, and then we are left with a situation where profitability is reduced again. So we have to be aware of the cost of the fertilizer and the value of the product. And we see that over time in this graphic here, that the cost of value threshold, this is the amount of, in this case, corn grain that can be that should be produced to cover the cost of the kilogram of nitrogen. So one has to produce at least, say, 5 kilograms of grain to cover the cost of a kilogram of nitrogen. I don't know the actual value for sugarcane because I don't work with sugarcane, but the thought process would be very similar in that the value of that product has to exceed, you have to get enough out of that fertilizer investment to cover the cost of that fertilizer. And only at that point is one making money. And if you want to make money, then you have to have high production at a low input cost. But we see that over time, this threshold is increasing, irrespective of the source of the fertilizer. So ideally, plants respond to nitrogen in a nonlinear manner. And in this case, the nonlinear manner would be that there's an increase, a dramatic increase that occurs initially, and then it starts to plateau with increasing rate of nitrogen availability. So the relative yield is a function of available nitrogen. If there is no available nitrogen, there will be no yield. If there's sufficient available nitrogen, then the yield can be optimized or maximized. But how we define the available nitrogen is really important as well. We can measure inorganic nitrogen in the soil, and oftentimes we measure it in the surface soil. We can also measure it residual in the profile. In some cropping systems, there's significant carryover of nitrogen from one crop to the next. I don't know the case in sugarcane, of course, being a perennial plant, it likely doesn't have a whole lot of residual, and if it is residual, then it's being utilized. But the issue is that inorganic nitrogen can be measured, but we oftentimes don't really account for the organic nitrogen, partly because it's just been simply difficult to actually assess, well, what is the impact of that organic nitrogen on nitrogen availability? So we can have a long-term stable nitrogen pool, or we can have this biologically active portion of the nitrogen as well. So if we had a site with low nitrogen availability and we apply fertilizer, we get a very large yield increase to that nitrogen application, and that means that profitability will have increased, almost assuredly. But there are cases where we have high available nitrogen, if we characterize that available nitrogen appropriately. Then applying fertilizer to that situation leads to very little yield response to that fertilizer application, and essentially we're losing money, but we're also damaging the environment in the process. So we don't need either one of those. And so it's best to define available nitrogen in some sort of manner. And so we need to have a way to do that. Our goal in agricultural production systems would be to increase the health of the soil significantly so that we could actually keep more of it in the more of that nitrogen in the organic form, and that it leads to greater production over time. And so we want to avoid that leakage, but we want to build up the biologically available nitrogen so that it can be more sustainable for the future. So in the research that I'm going to describe to you in the past 6 to 7 years that I've worked on this, and I characterize surface inorganic nitrogen and the biologically active portion of that organic nitrogen pool. So that's where I'm going to focus this effort here. So not all fields have the same available nitrogen in them. So again, we start with this ideal diagram of the relative yield versus available nitrogen. And some fields will, if we make the calculations, we can see that we can get approximately 20% of the relative yield if we didn't add any nitrogen fertilizer. That means that some sort of nitrogen was available to the plant and that we should be able to characterize it. And if we characterize it, in this case here, this is for an example of 10 tons per hectare of corn grain yield, that in this case here at 20% of the relative yield, that meant we should have had from the inorganic and the organic pools, we would have had 50 kilograms of nitrogen per hectare that was somehow being supplied through the soil component. We would have to characterize where that actually came from. Was it in the inorganic nitrogen or was it in the organic fraction? Well, there are other fields where we can actually see that without nitrogen input, we might achieve 60% of the relative yield. That means that effectively, that field would have a supply of nitrogen of 150 kilograms of nitrogen per hectare. And so we can see that these two fields would be behaving very differently in the organic the organic or the inorganic nitrogen supplying capacity. And we would have to define what are those components there, those subcomponents within this available nitrogen pool. A third example would be that, and we do see these occasionally, is that there are fields where if you don't apply nitrogen fertilizer in a check strip, and we get 90% of the actual optimized yield, that means that we have a large pool of available nitrogen, and most of the times it comes out to be the organic nitrogen rather than inorganic nitrogen in the soil. Because again, the inorganic nitrogen is susceptible to loss. It can be leached, it can be volatilized, it can be denitrified, it can run off. So these three cases that I've given you here suggest that the soil has an inherent capacity to supply nitrogen. And when I say inherent, it's due to management history as well as the inherent soil properties. So I wanted to get right into some of the results, because this is where I think that the interesting aspect is, like, how can we actually define these pools of nitrogen? So in this case here, I started this was from years 2014 to 2016 throughout North Carolina and Virginia on farmers' fields where we were looking at corn grain yield response to nitrogen fertilizer application. The Blue Ridge region tends to be here in the west. The Piedmont is in the middle, and then the coastal plain is on the right side here near the ocean, the Atlantic Ocean. Well, the results were that we found that that the relative yield was at least associated with residual inorganic nitrogen. Those sites that tended to have higher residual inorganic nitrogen did have the greatest relative yield. And those sites with very low residual inorganic nitrogen tended to have the lowest relative yield. The relative yield is the check strip, the strip without nitrogen fertilizer during the growing season that was allowed to produce and compare with the strip of corn that was receiving the maximum amount of nitrogen applied. Well, we can see that from this relationship, there's a large increase that occurred with only about a 50 kilogram nitrogen application. This is really unrealistic that we can actually get such a large yield return from a small increment of nitrogen application. So there was this positive effect, and there was significant residual inorganic nitrogen present, but it's not likely that this was all due to residual inorganic nitrogen. So if we now plot the same data of relative yield against net nitrogen mineralization, or the cycling of organic nitrogen to inorganic nitrogen, the process of microbial decomposition of soil, the mineralization of organic nitrogen to inorganic nitrogen, we see that there's a little bit stronger association, and that it actually tends to make a little bit more sense, is that we actually get this response probably more from the organic fraction of nitrogen in the top 10 centimeters than that of the residual inorganic nitrogen. So this nitrogen mineralization potential from the organic matter is likely to be a significant pool. And in the next case is where the summation of the residual inorganic plus the net nitrogen mineralization of the 0 to 10 centimeters is added together there, and then we plot that against relative yield. We get a similar association as with net nitrogen mineralization, but we see that it's probably more likely that that effect is really due to this nitrogen mineralization potential that occurs in these soils. And I must say that the reason that we get some sort of relationship like this is because, of course, I was focusing on those growers that are adopting a conservation approach. They're building up the organic fraction in the surface 10 centimeters. This was an intent to actually look at those producers rather than just the mainstream, those that were using a conventional approach. So if organic nitrogen mineralization is known, then that residual inorganic nitrogen really didn't provide a whole lot of benefit, because we could explain most of it with the net nitrogen mineralization itself. Well, soils are different, and we know that. We can see them when we collect samples from different regions, and regions, farms within a state or a province, we know that nitrogen mineralization is a biological process. Soil microorganisms are the key to mineralizing nitrogen in the soil. There's nitrogen that's present. We can have 1,000 kilograms per hectare of nitrogen in the organic form, but it won't be available to the plant unless the microorganisms consume it and release that nitrogen into an inorganic form. There's a stoichiometric relationship between carbon and nitrogen, and generally that relationship suggests that there are 10 parts of carbon that are released for every part of nitrogen that would be released. So this is an observation that has a long history. We know that the stable organic matter association is around 10. It can be up to 15 in many cases, and even higher in very natural systems. So nitrogen transformations can be equally divided between mineralization and immobilization. Mineralization, again, is the transformation of nitrogen from the organic form to the inorganic form. Immobilization, on the other hand, would be the transformation of inorganic nitrogen and back into the organic form. So it's taken away from the soil solution and put back into the organic matter. This can occur, and both of these processes often occur simultaneously. So this is why, even after 100 years, thousands of scientists investigating this, that we really have a difficult time of actually estimating net nitrogen mineralization, because it's complicated. So carbon transformations are dominated by mineralization and less by microbial biomass accumulation. The microbial biomass can fluctuate, but oftentimes it stabilizes. It can increase slowly over time, and it can decrease slowly over time. So in a lot of ways, carbon means that we can measure just the mineralization component, and we don't have to be so concerned about the immobilization part. Plus, it's 10 times greater in quantity than that of nitrogen. And so that gives us an advantage. Well, maybe if they're so intimately associated, if we want to estimate nitrogen availability, perhaps we could just measure carbon. It's 10 times greater in quantity that's being produced. So it's easier for us to actually measure. And it is dominated by mineralization rather than immobilization. So a shorter-term carbon mineralization assay might be possible for routine and rapid soil analysis. Well, this is actually starting to be done in the United States. I don't know about other countries, but we're actually starting to use this as a tool that could help us understand, in a broad sense, does this soil have a particular nitrogen supplying capacity? And that we could actually maybe reduce nitrogen fertilizer applications in the future. So soil test biological activity, and it's defined very strictly by the standardized methodology that is proposed. It's a simple, rapid, and robust indicator of soil organic nitrogen availability in agricultural soils. It is likely to be able to be used in natural soils too, in non-agricultural situations, but the focus here is on agricultural soils. And it is a simple test. It's relatively rapid. I can get you a number within a week, from sample submission to actual getting the number, because there are some steps in between there. And it seems to associate with nitrogen mineralization and nitrogen availability in the field. And I'm going to explain what the reasons I can make that statement. But first, what is soil test biological activity? Actually, what we're trying to measure is, through this assay, is carbon mineralization. We measure carbon mineralization during an incubation period. We optimize the temperature and the water conditions of the soil, and we measure carbon mineralization over time. Well, that's the research aspect of it. So the flush occurs because we've dried the soil, and then we re-wet it, and there's this burst of activity. The sugars in the organisms are being released, and they're being consumed by the neighbors that survive. And then after a period of time, there's a basal respiration that occurs. This is a steady state accumulation that occurs. You can see that there's a difference between, say, the 0 to 10 centimeter depth, the 10 to 20 centimeter depth, and the 20 to 30 centimeter depth. These are not absolute, but in relative terms, these often always occurs, that the respiration is greatest at the surface, 10 centimeters, and then tends to decline with depth, because the resources are different at these depths. So simply, the test is a very simple canning jar. We have 1 liter canning jar that can be rubber sealed with a lid. We have soil that's put in there in these 2 containers here. This is a bottle of soil, and here's another bottle of soil. And then we have an alkali trap, which consumes the weak acid of carbon dioxide, which is emitted and then trapped into this vial. And then we can actually measure. So that's just a little bit of detail about the method. Some key considerations here are that we need to represent the field of influence. We need to get a good soil sample. When it's 10 centimeter depth as recommended, then we need to get 10 centimeters. We shouldn't go down to 20 centimeters. So we have to define that depth. We have to oven dry the sample. This is just to normalize the conditions for all the samples so that we can get a good response from each of the samples. We could actually just air dry them, but it's preferable to oven dry them in this case. We sieve the soil coarsely because in many of our clay soils, we have significant aggregation, and we want to preserve some of that aggregation. We re-wet the soil to 50% water-filled pore space, and we incubate at 25 degrees Celsius for 3 days. And then we have an accurate determination of the amount of CO2. And in the case in my lab, we determine an alkali trap through titration. Others might use a gas chromatograph or an infrared gas analyzer. So those procedures are well known as well. Well, I wanted to share some data here with you to give you some sense that, well, it doesn't really matter where this soil test might be used. So these cases are where we have soil test biological activity along the horizontal axis, and we have the basal soil respiration along the y-axis. And we can see from these 3 different regions where I've selected soils from each of these regions, where we have the western United States, which should be characterized as relatively warm and dry. The tropics, in this case, Sao Paulo and Guam, would be relatively moist and warm, whereas the eastern United States would be moderate temperature in most of these cases, maybe a little warm in all these states, and also very wet. But it didn't matter where those samples came from. The association between basal soil respiration and soil test biological activity was essentially the same. There were slight differences in the slope, and that's indicated by the numbers here of 0.06 versus 0.05 versus 0.057. And those are slight variations, but essentially the same association would occur. And we can see from other data from North Carolina and Virginia, we have the soil test biological activity. So these numbers are going to become important later in the presentation of 0, 100, 200, 300, 400, 500, 600. This is the range of typical agricultural soils in the eastern United States that I've seen. We can get a little bit higher than this, and certainly we can get higher in some natural systems. But in the top 10 centimeters, these are normal values for agricultural soils. And what I've tried to do here is relate it to the actual net nitrogen mineralization that was measured in the soils over time, over 24 days during an optimized incubation. So we would prefer to measure net nitrogen mineralization. It just takes too long to actually get a soil test value back to a grow. We can do this soil test biological activity in 3 days, and essentially, safeguarding that with a week turnaround time to say that you can get a value within a week rather than over a couple of weeks or even a couple of months in this case. But the association was very strong in soils that were relatively coarse textured, where we had less than 20% clay. If we added those soils that had a medium texture, we get a very similar association. And then other soils that had greater clay concentration, well, a finer texture, they led to a very similar association also. So we could end up with one relationship that would be able to tell us what is the net nitrogen mineralization if we knew the soil test biological activity. And we get an R squared. This indicates the probability that these data fit this association. It's not really the probability, but it's the relative fit of the data along that single line that is shown there. And we see that 87% of the variation in soil test in net nitrogen mineralization could be predicted by soil test biological activity. So this is a really strong association. So this biological activity is the simpler, more rapid approach to estimating mineralizable soil nitrogen. Well, if we go back to the field and actually look at some of the yield responses now, let's actually look at some of the yield responses from these same fields that we conducted nitrogen trials in 2014 to 2016. This graphic here is an important graphic in that it was one of the first ones that I discovered, and I was actually shocked when I found these data. This is the grain yield response to the initial dose of nitrogen fertilizer. So from a yield response curve, if we actually plot what happens to, say, 10 kilograms of nitrogen on yield, and we see that if there's a large increase with that first application of nitrogen, we get a large yield response. That means that the crop was starved for nitrogen. It needed that nitrogen. However, if the yield response to that first increment of nitrogen is very low, it means that the plant really had enough nitrogen there. Adding more nitrogen didn't really add that much more to the yield potential. And surprisingly, this grain yield response to the initial dose of nitrogen fertilizer was highly related to the soil test biological activity. And this is, a simple test that's taken from a single soil sample and related to something that happens in the field in a complicated experimental design. So this, again, just to reiterate, these values here on the left would suggest that an increment of nitrogen yields a very large increase in grain production in this case. Again, focusing on corn, but probably applicable to many other commodity crops throughout the world. And these values here in the middle give a moderate increase in grain production per unit of nitrogen, whereas those at the far right would give a very small increase in yield to an increment of nitrogen. And so these data were important to actually illustrate that maybe that we could actually characterize biological activity and get an estimate of nitrogen availability. So the data are summarized here now as the nitrogen factor for economically optimum production of corn grain. So in general, we would expect that corn grain absorbs about 25 kilograms of nitrogen per ton of grain. So that value up here is kind of a theoretical value. That's where we should actually see it. So the line actually approaches that when we have very low biological activity. So meaning that we would have to apply all of the nitrogen as fertilizer. Whereas if we get these values that are down here, when we have a soil value of 500 parts per million of soil test biological activity, we get this very low need for additional nitrogen fertilizer. And so these data right here are compelling to say that the typical nitrogen recommendation is to average the soil conditions and say, well, you need to apply approximately 20 kilograms of nitrogen per ton of grain that you will expect to produce. Again, for sugarcane, it would be per ton of material that you're harvesting. And so this typical nitrogen recommendation would actually lead to under-fertilization in some cases, and probably over-fertilization in many. But the over-fertilization is more common in this scenario here. Well, I wasn't convinced, so I went out and tried it again. We need to get more data. So in 2017 and 2018, we conducted 111 field trials over 39 counties, a little bit broader swath in the same region though, but we wanted to actually document this a little bit better. Well, the results are that we didn't find a whole lot of difference in the yield response to that fertilizer. We saw that there was still this strong association, or relatively strong. It's not a perfect association, but by any means, but it is indicative that yes, a soil with higher biological activity leads to greater nitrogen mineralization. And so again, we see that typical nitrogen recommendation is probably good for that average condition where we're assuming that this is the average condition right here. But in these cases where there's greater biological activity, where farmers are adopting conservation approaches, where they're building the soil health of their system, they may actually be able to reduce the nitrogen fertilizer input. And so then economically, they're better off in the end. Well, we also looked at this in fall stockpile tallfest. It's not something that you're familiar with because this is frozen water on a grass crop here. I know it's something that maybe some of you have seen when you've traveled, but in our case, we get this in the wintertime. And I wanted to test this out because I'm curious about perennial grass systems as well. And essentially the data were that we get a similar response curve. And again, I want to just point you to this reduced nitrogen fertilizer required to optimize that fescue production with increasing biological activity. That's the point here. We do have a considerable scattering in some of the data, but we do see that overall there's this general association that occurs, and that forages, perennial forage in this case, responded very similarly in an association as did the corn grain. So the typical nitrogen recommendation is to apply approximately 60 to 100 kilograms of nitrogen per hectare, and that fits for what we would assume as a very low soil test biological activity. But that is not our condition in many of our pastures these days. We have pastures that are more in this range here of 300 to 400 to 500. That's where a lot of our pastures are. So the recommendation is probably too high, and that producers could actually reduce their nitrogen fertilizer application and then lead to greater profitability. They cut their fertilizer dollar cost, they reduce their input cost, and then they're increasing profitability. So the concept is ready to go, really. The standard approach is to apply this factor of 1, where the nitrogen factor is approximately 1. In this case, I'm just using it as a relative. In corn grain production, it's 1 pound of nitrogen per bushel, but in this case, it's just a relative yield case. But the soil health approach would suggest that if we can increase the biological activity of soil, then actually the amount of nitrogen needed in the fertilizer input would be much less. So there could be this condition of suboptimal nitrogen application in some case, small number of cases, I think, very small number of cases. But this superoptimal nitrogen application in a vast majority of cases, if in fact we can actually improve soil test biological activity. This is not a magical thing to reduce or to increase soil test biological activity. One needs to take the effort to be able to do that. It takes a conservation approach. We need to disturb the soil less. We need to keep the soil covered. We need to have these growing roots year round. We need to use our organic resources on the farm effectively and put them onto the land. So in many cases, this rather than a linear association, we might have a nonlinear association, and the effect would be similar. So it fits the model that I've had the premise for this research. That's actually, it's an inverse model, but it shows that it's actually following it, is that with high biological activity leads to high available nitrogen, and that can reduce environmental impact. Okay, I want to carry you through a little bit to the end. And in this case, I'm summarizing the number of field trials. So what I'm trying to do now is to bring this to a soil testing domain, where we could actually, rather than the exact number of 351 or 345, I want to give you a category. And so in this case, I had 159 field trials, and I wanted to divide them up. And logically, it made sense to divide them up into units. In this case, it was expressed as every 125 parts per million, milligrams of carbon per kilogram for 3 days. Every one, this is at 125, this is up to 250, this is up to 375, this is up to 450, and then anything greater. So dividing up all of the field trials into these categories. 5 categories we often use in soil testing: very low, low, medium, high, and very high. It's a simple approach. That way the growers are able to understand, if my soil test biological activity were high, I have a pretty good likelihood that I have a high nitrogen availability. However, if the soil test value comes out low, I have a pretty good likelihood that I need to buy fertilizer and apply it. So these are the data when they are expressed per category: the very low, the medium, the high, and the very high soil test biological activity categories across all the 159 locations. So, and then on these locations where we had the relative yield, there was a pretty good relationship that actually approximated the theoretical relationship between relative yield and available nitrogen. Well, we substituted soil test biological activity in this case. And so there's this strong association that occurs. These data also are mimicking those that were collected from individual field trials, where the grain yield response to that initial dose of nitrogen fertilizer. Again, if we had low biological activity, we should expect a very large increase in yield because the crop is starved. But when we have high biological activity, we have a low yield response to the increment of nitrogen, that first increment of nitrogen. And so is it really responsible for us to actually apply nitrogen in some cases? Again, here are the soil test categories for biological activity. We see that they can fit onto this curve here. And now this is the part where I'm taking this and actually make it into a recommendation domain, where we have this level of response per unit of these categories. Well, I can't stop there because it's a little bit more complicated than that. And of course, I'm not going to make it even as simple as or as complicated as it really could be, because the field situation is very complicated. We need to know the cost to value conditions that are out there. We can have low nitrogen cost and high grain price, and that means that the threshold might be low. We can also have a medium threshold where the nitrogen is the same and the grain price has decreased, or the nitrogen price has increased and the grain price is also high. Or we can have a very high cost value threshold. So the cost value threshold changes the slope of the curves that I'm going to show you. So again, this is at the low cost value threshold. These are the data that the yield responses came out to be. And then when we add in the medium cost value threshold, that means that all of the yields, well, not the yields, but the nitrogen factor has to be reduced because we need to produce more per unit of nitrogen. And that means that we can't do it once we're at the top of the curve. And so everything gets reduced. And I wanted to just kind of leave it like this in the simple diagram where the cost of value threshold, the conditions that you face on a daily basis, or you have to project through the growing season, what is the cost of fertilizer versus the value of the product, that might change. And so there's risk involved in agriculture, as all know in agriculture. But this has to be projected into the future to know what is the probability that we're going to have a cost of value threshold of low, medium, or high. And so these then can be put onto a categorization as well. And we can see that if the soil test biological activity on a field within a farm is very low, then we might have a relatively low need for nitrogen when the cost of value threshold is high. When the cost of value threshold is medium, we need a much larger rate of nitrogen fertilizer to economically optimize grain, in this case, grain production for corn, sugar production for sugar as well. And then it would increase even more with this low cost of value threshold. So you can see the sensitivity of the cost of value threshold is extremely high, probably even more of a range here when the soil test biological activity is low. So it begs the question, should we not be trying to reduce that variability by having better soil? You're given soil first, right? You buy land and you are given the conditions, but you can change the soil health conditions of the soil. That's the value that you can provide to your land. And so that's a place where if we can increase this soil test biological activity considerably, then that variation becomes much less and you get more certainty that you're going to be in an optimum range. So in sugarcane production, I don't know. I don't have any experience. I've only been to the edge of a sugarcane field. The question I have is, do soils behave similarly under sugarcane production as in corn production? Well, we might say that they might behave differently because, of course, the environmental conditions. Or it could be that the actual management of that crop is significantly different, that the soil could behave differently. So there could be some testing that needs to go on. Could the yield and the quality responses be similar? Well, I think this example in corn production actually gives you some hints as to what it could be in sugarcane production, but I think that's something that still needs to be tested as well. And could an existing databases be useful? Well, there could be some databases that you have in your region that are useful, but if no estimate of the mineralizable nitrogen pool has been measured, then it would be difficult to actually say an existing database is so useful. But that database that you might have could be useful in identifying the locations of where you can make some trials to actually make this development in the future. So I think there's a need because nitrogen fertilizer cost is high, environmental degradation from nitrogen application occurs, and profitability is so linked to nitrogen fertilizer application. So it's a three-way avenue there. So in summary, I wanted to say that soil health is really a vital underpinning of sustainable agriculture. Whatever we want to call it, sustainable agriculture or regenerative agriculture, soil health is really a part of that. Our soils are a vital natural resource, and we need to rely on them. We shouldn't damage them. We should actually increase their functional attributes. Soil test biological activity is a simple, rapid, and robust indicator of soil nitrogen availability. The data are pretty clear. It's not perfect, but the data are clear that it's simple, it's rapid, and it does indicate soil nitrogen availability. We're not measuring nitrogen availability with the test, but it still indicates soil nitrogen availability. And profitability and environmental quality can be improved with field-specific assessment using soil test biological activity. I thank you for your attention, and I appreciate again the invitation by Fernando Munoz for the opportunity to be with you, and I certainly wish I could see some of the faces in this crowd of 1,000. Thank you so much.
Gracias, profesor, por su presentación. A los participantes, recuerden que las preguntas pueden ser enviadas a través del aplicativo, del código QR que se presentó en la pantalla. Tenemos algunas preguntas, así que vamos a aprovechar este momento y sobre la marcha, si tienen adicionales, por favor, tengan la libertad de enviarlas. Así que, haciendo uso de la tecnología, vamos al aplicativo. Bien, profesor, ¿listo? Vamos con la primera pregunta. ¿Cuán aplicables serían estas metodologías a la caña de azúcar que tiene un ciclo más largo que el maíz?
Sir, can you hear me?
I can hear you.
Oh, thank you. I am going to repeat.
¿Se le transmitió la pregunta, profesor?
Okay, thank you.
Question.
Okay, professor, just 1 second. There is a technical issue. Bien, vamos nuevamente. La pregunta es, ¿cuán aplicable serían estas metodologías a la caña de azúcar que tiene un ciclo más largo que el maíz?
Yes. Okay. Thank you for the question. I think it's very important. Of course, I gave you the example of corn, and I want to apologize, but I can't apologize because I have no experience for sugarcane and I don't have any opportunities. And I understood, but I think the reason that the concept is still valid is that I've looked at this in fescue, which is a perennial grass as well. Of course, it grows in a different environment. The issue is that soils are inherently, we have very similar characteristics or processes that occur. Nitrogen mineralization occurs through the biological activity, the microorganisms, the bacteria, and the fungi that consume the organic resources. And sugarcane, being a perennial plant, it has roots that are penetrating the soil. It has residues that are falling to the surface. So the conditions are really quite similar to any other plant, and corn being a C4 plant, similar like that, gives it some strength in association. The issue with, of course, there's not the seasonal attributes, say a dry period versus a wet period. Those are what control pulses of nitrogen that might be released from the soil. Sometimes it's important for a dry period to actually precede a wet period so that a pulse of nitrogen availability could occur. If the plant isn't growing, though, at that period, then it could be lost to the environment. So my answer to the question would be that I believe that there's plenty of conceptual synergy between corn and the sugarcane. It's just, but the environmental conditions, I understand, are going to be different. And you may have sugarcane grown on some highly moist soil, wet soil, that would be, of course, lead to nitrogen transformations that I can't necessarily predict. And so I think it's a scientific effort that would need to occur, that people have to actually just test it, make sure that the associations could be developed. Not the associations first. I think we need to get estimates of nitrogen mineralization differences between fields. And when I say between fields, yes, between fields that are inherently different, but also that are managed differently over time. That's where the range of conditions would be necessary for the scientific effort to actually understand, could this actually be something that predicts the environmental conditions that soils face? So I believe that there's good possibility, but there's testing that's needed.
Gracias, profesor. Vamos a la siguiente pregunta.
Thank you, professor. We are going to the next question.
¿Hay límite para aplicar nitrógeno en caña de azúcar?
To apply nitrogen to sugarcane? Is there a limit?
I'm sorry, could you repeat, please?
Yes, sir. Is there a
limit? ¿Hay límite para aplicar nitrógeno en
Is there a
caña de
limit
azúcar?
to apply nitrogen to sugarcane? Is there a limit?
Is there a limit? Again, I don't have experience in sugarcane, but I would say yes, there should be a limit. The growth capability of any plant has limits of the environment. It has limits based on the temperature, the water, the available sunshine, the activity, the root system of able to extract nutrients. And so nitrogen is often the most limiting. So there should be a limit as far as productivity. Now, and I'm sure that the sugar concentration is affected by nitrogen too, that maybe excess nitrogen isn't always the best for sugar quality or the quality production so that you optimize the output. So yes, I believe there's a limit, but I don't know the limit.
Gracias, profesor. Siguiente pregunta.
Thank you, professor.
¿Cómo podemos incrementar la actividad biológica del suelo?
The question is, how can we increase the biological activity on the soil?
Disculpe, profesor.
Yes, great question.
Tuvimos un problema técnico.
We apologize,
that's
Repito la pregunta.
Okay, no worries. Yes, it's a great question, because that becomes the issue. How do we go take away this information from this seminar and into the field? What can we do? Well, it's really what we've seen, at least in North America, is that we need to disturb our soils less. That allows the aggregates of the soil to build up the organic resources so that this carbon and nitrogen, these compounds, are sequestered within the aggregates themselves. This is important so that, of course, the soil functions better with a undisturbed soil over time. It may be not the first year, but the over time, soils function better when they're less disturbed. And so disturbing less is really important. Then the next step would be that we need to make sure that organic resources become available to the microorganisms. Essentially, we need to feed the soil. Feeding the soil means that roots of the plants, and sugarcane being a very robust plant, is a very good thing for it. So the roots of the sugarcane will be excellent for secreting carbon compounds to enhance the biological activity. But once, if those roots are disturbed, then things disappear. And so we want to build up the organic reserves in a slow manner, because there will always be decomposition, but over time, we can build up the organic fraction and the biologically active organic portion. And so adding the crop residues are very important. I don't know what the conventional management system is, but I know that, often sugarcane is burned. I understand the need for it, but it actually, we lose a lot of our nitrogen and carbon through burning. And so we're losing the potential over the long-term potential of a system by having burning. So if there's any way to burn less, this would be a good thing. So those residues are important. Then if the field has the opportunity to be rotated into different plants, crop systems, then it's possible that other specific crops could actually add more or a diversity of those organic resources, and that could be a very good thing. Thirdly, there could be an option of adding additional organic resources, such as animal manures or industrial byproducts from sugarcane itself, back to the soil, because any carbon compounds are food for the organisms in the soil. If we want to feed and build the biological activity, we have to feed them. We have to give them resources. And so those are the points that I would make as the strongest is really soil disturbance, and then making sure that we feed the soil with carbon resources.
La siguiente pregunta guarda relación con anterior.
Can you hear me, sir?
Es, ¿cuáles microorganismos contribuyen más a hacer
microorganisms contribute more for the soil? Which microorganisms contribute more to the soil?
One more time, please.
¿Cuáles microorganismos contribuyen más a hacer disponible nitrógeno del suelo?
To lead to availability of nitrogen to the soil. Which microorganisms?
The
availability of nitrogen to the soil.
I understood the question as which microorganisms contribute more to the nitrogen availability of soil.
Yes.
Is that correct?
Sí.
Okay.
Right.
We'll take that question as which microorganisms. Well, there's a great diversity of microorganisms in soil. We have species that are far outnumbering our capacity to actually identify them. So we don't know which ones are purely responsible, but the issue is that many of them are contributing, because the issue is that bacteria and fungi, which are the dominant groups that would be performing this operation, and in general, bacteria are more numerous and more active than fungi. Yes, fungi are important, and perhaps we can change the bacterial to fungal ratio, but this is something that is very difficult to overcome the natural limitations of the environment, moisture and temperature. So in general, I would say that all of both bacteria and fungi they are like people. We need to eat, and then we respire. And on a daily basis. We need to have this daily. We can't just go without a month. And microorganisms are kind of like that too. They need to have a daily feeding of food so that they can produce. They can replicate, so they are able to have more of those organisms there. So I would say that it's both bacteria and fungi. There are actinomycetes as well. But to name species of them, I'd be hard pressed to name them, because almost all of them are heterotrophic, and that heterotrophic nature means that they have to consume these organic resources, and they are then releasing nitrogen through that process.
Gracias, profesor. Tenemos un par de preguntas más para ir concluyendo. ¿Qué tanto se puede disminuir la dosis de nitrógeno en el suelo, teniéndose en cuenta que hay una cantidad importante que puede ser disponible?
Would you like the question to be repeated, sir?
I'm sorry, could you repeat?
Can you hear me?
I can hear you now.
Good.
¿Qué tanto se puede disminuir la dosis de nitrógeno en el
of
suelo,
nitrogen on
teniéndose
the
en
soil,
cuenta que hay una
taking into
cantidad
account that there
importante que
is an
puede
important
ser
amount
disponible,
could be available,
puede ser o estar disponible.
could be available there.
I'm sorry, I didn't quite understand the question.
¿Qué tanto se puede disminuir la dosis de nitrógeno
How much,
en el
which
suelo, teniéndose en cuenta que hay una
amount of
cantidad
nitrogen on
importante
soil, taking into
que
account that
puede
there's
estar
important
disponible en el
amount
mismo suelo?
on the soil?
I'm not sure I understand the question, but how much nitrogen from fertilizer is, I'm sorry?
Si quieren pasamos a otra.
Continue, sir, please continue.
Profesor, la siguiente pregunta.
Well, as I understood it, how much nitrogen might be needed beyond that, which provided by the soil, perhaps. Again, this is dependent on this would require scientific investigation. One would have to create trials on soils that have different capacities of nitrogen supplying capacity, and then find out what is the yield response to that. And that's essentially what we did in corn. We were taking different soils that had different nitrogen supplying capacity. Some of them had only supplying capacity of 50 kilograms per hectare. Others had 150 kilograms per hectare, and some had 300 kilograms per hectare of nitrogen supplying capacity. By putting a scientific trial on these fields, we can determine, well, if the soils have different nitrogen supplying capacity, theoretically, conceptually, we should actually see a reduction in nitrogen fertilizer need with those soils that had higher nitrogen fertilizer or nitrogen supplying capacity. And so this requires scientific investigation. We need research trials where we have a very strict protocol that we have the similar conditions under all of these different field conditions. Similar experimental protocol for all of these field conditions.
Gracias, profesor. Con esto cerramos la sesión de preguntas y respuestas. Profesor, le agradecemos por acompañarnos virtualmente hasta Cali, la sucursal del cielo. Por favor, un aplauso al profesor.
Thank you.